Hello friends, welcome to another tutorial in Analog Electronics series. In this tutorial we'll talk about feedback amplifier connections. And in the previous tutorial we talked about different types of amplifiers, the classification of amplifiers based upon whether they're voltage amplifier, current amplifier, transconductance amplifier and transresistance amplifier. They are going to be supremely important in this tutorial because one of these amplifier is going to fit into the basic block diagram of the feedback amplifier over here. So the basic amplifier, which has a forward transfer gain of A, will feature any of those four amplifiers. So it's supremely important to see that video first before you proceed on with this one. So if this is something that interests you, then please keep watching. Alright, let's talk about the basic block diagram of a feedback amplifier. The concept of feedback has already been discussed in a previous video. You could watch that video for a better understanding of what a positive feedback is and what a negative feedback is, and how is positive feedback better than negative feedback, or how is a negative feedback better than a positive feedback. But here in this video we'll actually make a feedback amplifier with additional components being used. So when we talk about feedback amplifier, we know that essentially the center or the heart of the feedback amplifier will be an amplifier. So we'll see what kind of amplifier fits in what kind of a configuration. And then we have a sampling network. Please understand, this is a key term. Sampling network refers to the network which is going to take the output and will give it back to the feedback network with reverse transmission of beta. So sampling happens at the output. So its job is to take the output, whether in the form of voltage or in the form of current. So we'll see that. So sampling network can be classified on the basis of whether it is taking voltage and feeding it to the feedback network, or whether it is taking current or feeding it to the network. And on this side, at the input side, we have a mixer network, again a key term. And the job of the mixer network is to take the feedback from the feedback network and mix it with the incoming input signal. And in the concept of feedback amplifiers I discussed, this input could be mixed with the feedback in a positive way or a negative way, depending upon whether it's a positive feedback or a negative feedback. So again, a mixer can take up the signal from the feedback network in terms of voltage or in terms of current, depending upon whether what kind of a configuration is that. So all in all, if we talk about the permutations which we have, based upon what we take from the output and what we give at the input, we get 4 different permutations, and those are voltage, series, feedback, and then voltage, shunt, feedback, current, series, feedback, and current, shunt, feedback. Now please understand, with this nomenclature, the first term refers to the output that we take. So if you're taking voltage from the sampling network, so that will be featured here in the first place. And the second term will refer to the input. So if we are giving voltage back to the mixer network, we'll say it's series, and if we are giving current to the network, we'll say shunt. Well, how does that happen? I'll tell you in a bit. But the first term refers to the output, the second term refers to the input, and then the feedback amplifier. So that's how the nomenclature works. Now, having understood the 4 types of nomenclature that could stem out of this block diagram of a feedback amplifier, let's see how a sampling network can be classified. Now, as I mentioned, there could be 2 types of sampling. We could either take voltage from the output and feed it to the feedback network, and we could take current. So depending upon if we take the voltage, the connection will look something like this. And how can you relate this to the voltage sampling is that the voltage is always measured in parallel, right? So you take 2 parallel connections from the output terminals and feed it to the feedback network. That's how you can remember it. And you always measure current in series, right? So what you do is you break the connection at the output terminal and give it to the feedback network as you would have measured some current here. So that's how these 2 connections are labeled as voltage sampling and current sampling. But if you look closely, there is no fundamental difference at all. You still have that load resistance, you still have that output current flowing through that load resistance. It's just a matter of how the physical wires are being connected from the output to the feedback network. Now let's look at the mixing network. There could be some confusion in the mixing network because just by looking at this kind of mixing, we see that this is a series mixing because whatever is being fed is being fed in series with this entire input network, where here Ri will be there. But if you look closely, when you feed the output from the feedback network in a series fashion, what you feed here is actually some feedback voltage in series with the entire loop. So that is why the series feedback is also known as feeding voltage back to the mixing network. So very, very important point. If you look closely, when you feed the mixing network with series, you're actually developing some voltage in this series network. It could either add up to this Vs, or it could lead to subtraction of Vs, and this feedback, series feedback, is actually developing some voltage across here. And on the other hand, now the things will get clearer. This is the mixing network. If you feed shunt connection, you'll see that from this Vs, if some source current originates, some current will deviate in this path and the rest of the current will go into the Ri, which is the input resistance. So deviation of current means that the shunt feedback will feed back the current element to the mixing network. So the key point here is series feedback mixes voltage and shunt feedback mixes current. And the reason is pretty clear, that the series will develop some voltage here and the shunt will give us a path for a current deviation. So that's how the mixing networks are classified. And if we take up the case of all the permutations now, you'll see that when we take up voltage from the sampling network and we give voltage at the input, what kind of an amplifier would you like to use here? The answer becomes pretty clear that you would want to use a voltage amplifier here. And if we take up current from the output and if we give voltage at the input, what kind of an amplifier would you want to use? The answer would be pretty clear that you would want to use a transconductance amplifier, because transconductance amplifier, as mentioned in the previous videos, transconductance amplifier facilitates the current at the output and voltage at the input. So if you remember this logic, then it becomes very easy. Now guessing from the third figure, we see that we are taking current from the output and we are giving current mixing at the input, and taking current from the output and giving current at the input is facilitated by a current amplifier. And finally we are taking voltage from the output and giving current at the input, so that is facilitated by a trans resistance amplifier. And that is the reason why we use different types of amplifiers in different types of feedback connections. Although logically there is no difference, but it's just that the facilitation happens in such a way that if we are taking voltage from the output and giving voltage at the input, that logically means that a voltage amplifier will be more suitable or more aptly used. So that is how these connections are made, and these diagrams are super important if you wish to label them. So this becomes a voltage series, and this becomes current series, and this becomes current shunt, and this becomes voltage shunt feedback. So the nomenclature is, the first one is output and then input is series. However, the series input will drop a voltage here. The first term refers to output, which is current, and the second term refers to series connection, which develops a voltage here. The first term refers to current at the output, and the second term refers to shunt. Shunt will cause some current to be added or subtracted here at the mixing network. And finally, output, input. So output is expressed in terms of the parameter and input is expressed in terms of the configuration. So parameter is voltage or current, and the configuration is either series or shunt. But you need to understand what a series mixing means and what a shunt mixing means. And I hope with this discussion everything is pretty clear about the mixing and the sampling thing with the feedback networks. And this is very important if you wish to continue with the analysis of how the input impedance and the output impedances change with negative feedback and so on and so forth, that we'll discuss in the next video. So I hope you liked the video. If you did, give it a thumbs up, consider subscribing, share it amongst your friends. Take care of your health. I'll see you around in the next video. Take care. Bye bye.